Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 8. Computing Improper Integrals. An integral is referred to as an improper integral when the interval of integration, or the integrand itself, is unbounded. Computing such integrals presents certain challenges due to the behavior of the integrand at infinity or near singularities. Numerical integration is sought only when an improper integral cannot be solved analytically, or when it is difficult to find a closed-form solution. Numerical methods for improper integrals involve adapting standard integration methods to handle infinite limits or singularities. By selecting a suitable method based on the nature of the improper integral, one can obtain accurate numerical estimates for these integrals. Type 1 improper integrals are definite integrals that are infinite at one or both endpoints. That is, the integration interval is infinite or semi-infinite. Semi-infinite integrals are fixed at one end and extend to plus or minus infinity on the other end. For example, the following is the case where the integration extends to plus infinity. The next one illustrates an integral which extends to minus infinity. In the last case, both lower and upper limits extend to infinity. Type 2 improper integrals have integrands with a singularity within or on one or both endpoints of the integration interval, i.e., the integration interval is finite, but the integrand is unbounded. For example, in the following case, the singularity of the integrand corresponds to the upper end of the interval. In the second case, the singularity occurs at the lower end of the integration interval. In the last case, there is a singular point within the integration interval. Before attempting to approximate type 1 and type 2 integrals, if possible, try to remove discontinuities or make the integration interval finite by applying a suitable coordinate transformation. In order to avoid type 1 integrals over the semi-infinite interval, the two integrals can be transformed, provided that f plus or minus 1 over u squared is defined or has a removable discontinuity at u equals 0, as follows. Alternatively, when transformations do not work, an integral over a semi-infinite region can be split into two integrals as follows. Typically, fx is finite in a bounded interval such as from 0 to a, while fx is approximately 0 everywhere else. The first integral can be estimated by a suitable numerical integration method. The second integral can be approximated using a suitable coordinate transformation, such as x equals 1 over u or x equals a over 1 minus u, or ignored for sufficiently large a, which is referred to as truncating integral. Integration from minus infinity to minus b can be handled in the same manner as the ones from a to infinity. The semi-infinite improper integrals in the following forms can be computed using the Gauss-Laguerre method. See Video 9. The improper integrals over the whole domain having the following form can be estimated using the Gauss-Hermite method. See Video 10. Some type 2 integrals can be transformed to standard definite integrals using a suitable transformation that completely eliminates any discontinuity of the integral at an endpoint. For example, provided that fx is bounded over the entire range, pay attention to the u substitutions used in the following examples. For a bounded fx on the interval from 0 to 1, a discontinuity at x equals 0 of the following integrals is eliminated by a transformation, while the transformed integrals become the ones over a semi-infinite interval. These integrals may then be calculated using the Gauss-Laguerre method. See video 9. Definite integral of a function with closed Newton-Cotes formulas is based on the assumption that the integrand is continuous and defined on an interval. However, these rules cannot be employed to type 2 integrals, where the integrand has a discontinuity at the lower, upper, or both endpoints, or at an interior point. Open Newton-Cotes rules, on the other hand, do not include the endpoints of the subregions. They require the integrand at interior points. Thus, open Newton-Cotes rules may offer advantages in some cases, such as avoiding the need to evaluate the integrand at singularities or endpoints where the function may not be well behaved. The subtraction of singularity is a technique used in numerical integration to handle integrals where the integrand has a singularity or becomes unbounded at a certain point within the integration range. For example, consider the following integral, where k is a function with a singularity at x equals c. The singularity can be removed by adding and subtracting an integrable function from the integrand, forming two integrals, one with a removable singularity and the other that can be evaluated explicitly or numerically. In the following step, we add and subtract gc from fx under the integral sign. The first integral yields 0 by 0 indeterminate form, while the second integral can usually be integrated to eliminate the singularity. Let us consider the following integral having a singularity at x equals 0. We will be estimating the integral using the subtraction of singularity technique. We may express the integral as follows, where fx is cosine hyperbolic x. The function k is the function with singularity at x equals 0. To obtain a 0 by 0 indeterminate form, we add and subtract 1 to and from fx as shown. We get two integrals, one with a removable singularity at x equals 0, the other one, which is analytically integrable, yielding the result of 3. L'Hopital's rule for the singular point yields 0. Methods such as the trapezoidal or Simpson's 1/3 rules may be expressed as a weighted sum. Thus, to be general, we will replace the numerical integrations by a weighted sum. Note that the first term of the summation yielded 0 as a result of L'Hopital's rule, so we can recast the summation from I equals 1. When we carry out the calculations using Simpson's 1/3 rule with 10, 20, 40, and 100 panels, we obtain 0.224124 with n equals 100, which is at least 5 decimal place accurate. Recall that the first point in the numerical summation was excluded as a result of L'Hopital's rule. Finally, substituting the numerically calculated integral we get. Ignoring singularity approach is often applied to type 2 integrals with a singularity at the lower, upper, or both endpoints. It is a primitive way of treating singular integrals, as we circumvent the singular point by applying a numerical integration rule while ignoring the singularity, and we can blindly apply a numerical technique and hope for the best. The best results may be obtained using the Gauss-Legendre method or open Newton-Cotes rules, as they inherently avoid endpoints. This approach does not work well for the integrands depicting oscillatory behaviors. Let us estimate the following integral by ignoring the singularity at x equals 0. We will also investigate the convergence of the numerical approximations with the number of quadrature points and number of subregions using Gauss-Legendre method and the three-point open Newton-Cote rule, respectively. The 6 decimal place accurate true value of the integral is 3.224/123. Both methods can be expressed as a weighted sum. Using the Gauss-Legendre method, we evaluate the integral for 5, 10, 25, 50, 100, and 500 integration points. The results are tabulated as shown. For n equals 500 points, the Gauss-Legendre method converges within 0.91% error. On the other hand, the three-point open Newton-Cotes formulas yield to a result within 1.5% with 10,000 subregions, which amount to 40,000 panels in total. It is clear that, despite all these computational efforts, the convergence of both methods is not very good. The truncating interval technique is usually employed for estimating type 1 integrals. An improper integral of f(x) on a semi-infinite region can be broken up into two parts, where b is a sufficiently large number. The first part can be estimated by applying a suitable numerical method. The second part represents the truncation error. If f(x) is not integrable in closed form, which is usually the case, an estimate for the upper error bound can be obtained by using an integrable function gx, which should be greater than f(x) and integrable. Now let us consider estimating the following integral by truncating the integration interval. We split the integral into two parts as follows. The first part will be calculated once a value for the upper limit b is determined. The second part, which is the truncation error, is defined as our b. To find an approximation for our b, we replace the sine-squared term with 1 since it ranges between 0 and 1, which also makes it greater than the integrand f(x) for all x. Now we integrate this approximation, which will give an upper error bound for the numerical integration for any b. Experimenting with several b's, we calculate and tabulate our b's as presented. Notice that for b equals 50, the upper bound r is less than 0.5 times 10 to the minus 3, which will ensure at least 3 decimal place accuracy when the integral is estimated with b equals 50. Of course, provided that the first integral is calculated with at least as much or better accuracy. The first part is approximated for b equals 50 and n equals 10, 50, and 100 panels using Simpson's rule, and the results are tabulated. It is clear that the estimate with 50 panels is 7 decimal place accurate. Finally, using this result, we obtain the estimate as 0.299/5865. With this note, we end this lecture. See you next time with another topic. Bye.